Hi there, welcome to my 5-image story. So this 5-image story is going to be about the general circulation of the atmosphere. And the first slide is about the direction of the wind. So the cause of the wind is unequal heating of the Earth's surface. In tropical regions, more solar radiation is received than is radiated back to space. In polar regions, it's vice versa. The Earth balances these differences in a special system. The direction of the winds is in accordance to warm air moving poleward and cold air moving toward the equator. This happens to attempt to balance out extreme temperature differences. Hi there, welcome. Next up, we'll be talking about the Coriolis effect. The Coriolis effect affects winds and currents. So, the Earth's rotation causes a deflection in the path of the wind. In the northern hemisphere, the Earth experiences a counterclockwise rotation. Therefore, the wind deflects to the right. In the southern hemisphere, it is a clockwise rotation. Therefore, the wind deflects to the left. We attribute this to the Coriolis effect. The Coriolis effect always directed at right angles to the direction of the airflow. It affects only wind direction, not wind speed. But the Coriolis effect is affected by wind speed. The stronger the wind, the greater the deflection. The Coriolis effect is strongest at the poles and weakens equatorward, becoming non-existent at the equator. The Coriolis effect is proportional to the wind speed, but the friction lowers wind speed, so it reduces the Coriolis effect. For my picture here, it says that the intended path is at the poles, but the Coriolis effect changes those paths to the right and to the left, as you can see by the arrows curving. So now that we've talked about the Coriolis effect, let's talk about what it looks like in the atmospheric circulation in the northern hemisphere. So in this photo, we see 3 different convection cells: the polar cell, the Ferrel cell, and the Hadley cell. More solar energy hits the equator, so air warms and creates a low pressure zone. At the top of the troposphere, half moves towards the North Pole and half moves towards the South Pole. Cooler air is dense, and so when it reaches a high pressure zone, it sinks to the ground. The air is sucked back in toward the low pressure at the equator. This just describes the convection cells north and south of the equator. Now we'll be looking at the global wind belts. As you can see, there are three different cells in this photo: Hadley cell, Ferrel cell, and the polar cell. The Hadley cell air should move from north to south, but the Coriolis effect deflects it to the right. The air blows from the northeast to the southwest. This belt is the trade winds. In the Ferrel cell, air should move south to north, but the winds actually blow from the southwest. This belt is the westerlies. In the polar cell, the winds travel from the northeast and are called the polar easterlies. The wind belts are named for the directions from which the winds come. The westerlies, for example, blow from west to east. These names hold for the winds in the wind belts of the southern hemisphere as well. So how does the general circulation of air affect the climate in some areas? Well, now we're going to be talking about monsoons. Circulation over the oceans is dominated by semi-permanent cells of high pressure in the subtropics and cells of low pressure over the subpolar regions. Subtropical highs are responsible for the trade winds in the westerlies. Asia becomes cold in winter and develops a seasonal high-pressure system from the surface flow that is directed off the land. In summer, the opposite occurs. Land masses are heated and develop a low-pressure cell which allows air to flow onto the land. These seasonal changes in wind direction are known as monsoons. The general circulation is produced by semi-permanent cells of high and low pressure over the oceans and is complicated by seasonal pressure changes over the land.